things in this one. Let's talk about what is a bipartite graph quickly. So let's say this is a graph G, and in general, bipartite graph, we can draw it that we put, let's say we have in total a graph of 5 vertices, and let's give an example of a bipartite graph on 5 vertices. So in that case, a simplest way to draw a bipartite graph is we can draw in one line here on the left one set of the vertices and the remaining vertices on the other side. The idea of a bipartite graph is you split up the graph into 2 subsets of vertices that together give all the vertices, but they have no edges between each other. So what we have here is we can now draw this example. So what can happen is each vertex from the left can connect to all vertices on the right. Each vertex from the right can connect to all the vertices on the left, but the vertices on the left cannot connect to each other by edges. The same goes for the ones on the right. So I can just complete what was mentioned here. I can just connect each vertex on the left to each vertex on the right. By that, automatically, I of course connected each vertex on the right to each vertex on the left. This goes for any amounts of vertices on the left and right. Also, the graph can be reorganized into different shapes. In a previous one, we, for example, talked about how even cycles, so cycles with even number of, graphs that are cycles that have an even number of vertices, are bipartite graphs also. So you can, of course, change, as far as drawing the graph, you can change the orientation of the vertices and edges in space to make it seem like something else, but the graph could be still the same depending on the case. So here we actually see a bipartite graph on 5 vertices, which wouldn't happen with a cycle graph, for example. There's also a theorem regarding bipartite graphs that talks about it can have no odd cycles, but that's a thing to discuss in another one because there's many properties that bipartite graphs have. But let's just do one thing, and that is, let's say we can call L and R the 2 sides of this bipartite graph. So we see the left vertices, the 3 vertices here on the left, we put in the subset L, the one on the right we put to the subset R, and it works out. The only condition that had to be fulfilled is these vertices within the one set, they're not connected to each other by any edge. And the ones on the right satisfy the same. Of course, if you change the position of these vertices, retaining the edge relations between the vertices, but shuffled up their spatial location, the graph would still be bipartite. It just wouldn't be as clearly shown by an image. We see it bipartite when we can clearly see that all the vertices are contained either within one or the other side, and within each side they are not connected to each other. So they act as disjoint vertices that have no connection of edges among each other in each of these 2 subsets. That's a bipartite graph.